Wave nature of matter. Today's outline: wave-particle duality of light and material waves. These are based on chapter 2 of Gangchen, as shown here. So you'd better read through chapter 2 of Gangchen. And there's also homework number 1 in the end of the slides. A wave is characterized by its frequency and wavelength. Let me use the pen here. Frequency, let's set it mu, wavelength lambda, and its energy E is determined by the frequency, so it is said to be h bar omega or h mu. H is the Planck constant, as you know. Planck constant. We also know that a particle is characterized by its energy, momentum, and momentum. Momentum is usually symbolized by P. Waves and particles are two completely different concepts describing matter and not related in classical mechanics and electrodynamics. In quantum mechanics, however, they are interrelated and are two aspects of matter. Two perspectives for different regimes. Let me use the pen. So two different regimes are summarized here. One is macroscopic, the other is microscopic, and corresponding energy levels are either continuous or discrete. Description of matter is either particle or wave. We often use particle picture or wave picture. And examples of modeling procedures are, in the case of macroscopic system, Fourier law, Newton's law. In the case of microscopic system, we see Schrödinger equation dispersion. So those two perspectives for different regimes or systems are summarized. For macroscopic systems, we take the continuity of many variables for granted, including the continuity in energy. Yeah, we are familiar with this concept of continuity in energy. That's what is written here in macroscopic system. For example, heat flux along a rod through conduction according to a Fourier law can be continuously varied to any desired value by controlling the temperature difference and the material properties. The asterisk is explained further here. This is discussed in the context of transport. Intuitive introduction is found in Gangchen chapter 1. I found this is very useful and intuitive. So in classical system, most of the cases in the macroscopic systems, the quantity such as heat flux is considered to be continuous. The microscopic picture of energy, however, is entirely different. According to quantum mechanical principles, the permissible or available energy levels of matter, such as electrons, crystals, molecules, and so on, are often discontinuous. Okay? Discontinuous, or we can call it discrete. Differences in allowable or available energy levels among materials are major factors that distinguish them from each other. For example, why is glass transparent in the visible light range but not silicon? So that's why, glass doesn't have a color, but silicon is not visible, not transparent in visible light. That's why silicon is black. And why are some materials electrical insulator, but others are conductors? These are the actually concept of energy band. Energy band, especially between the valence band, and conduction band, and their separation is called as band gap. And this band gap, Eg, can be replaced by h bar omega. Okay. Let me remove some of this. Okay. H bar omega. And depending on this frequency omega, or we can say that this is mu or h mu. Is the German pronunciation. This mu is replaced by the velocity, divided by lambda. So this energy gap is related with relevant wavelengths of any emitted light. Okay, so visible energy. It means visible is usually from red to blue. Blue is on the order like a 400 nanometer. Red usually on the order of like 700 nanometer. So if the band gap is larger than visible range, for example, then the light will pass through here. It is not observed by the transition between conduction band and valence band. Then we call it transparent. In the case of silicon, band gap Eg is around 1.1 electron volt. At room temperature, 1.1 electron volt. That's around like 1000 nanometer. This is IR. Okay, IR. So band gap is small. Okay, band gap is small. So visible light are all observed. Okay, So the light will be absorbed and replaced by electron excited into conduction band. So the light cannot pass through the silicon in the case of visible range. That's why it is black. In this way, if we know the difference between conduction band and valence band, we can describe the color of the materials. And in this way, we can also consider the insulator and conductors. Insulators, it means there are almost no electrons in conduction band. So it is very hard to excite electrons from the valence band to conduction band. In the case of conductors, there are enough electrons in the conduction band. So it is easy to be excited into conduction band. So basic idea is conductors usually has smaller band gap or almost no band gap. Insulators, they have large band gap. Well, glass we consider here, for example, it is transparent. So it means band gap is larger than visible range of light. We can see that. Also, glass is insulator. Okay, so band gap is large. The large band gap, which leads to the property of insulator. It is actually correlated with the color of the material. Okay, so those are all described based on quantum mechanics, because the energy separation between valence band and conduction band, it already means that energy levels are discrete. Okay, even though I said band and now I said energy levels, the difference will be discussed later on between levels and band, but they have similar concepts. Okay, so point here is the property of being discrete in energy is related with the color of the material, and those are all explained by quantum mechanics. Okay, if there's anything confusing, then you can have a question in the YouTube channel. Right. In this chapter of Gangchen, chapter 2, we introduce the basic quantum mechanical concepts necessary to appreciate various energy states found in different materials. It should be remembered that these energy states represent the range of possibilities for the matter, but do not tell which state the matter will be in. So it means that what kind of energy states are there will be described based on quantum mechanics. But still, it doesn't tell which state the matter will be in. Yeah. So this means that what kind of energy states are there? Let's say energy levels are discrete. And then which energy states are filled? Okay. That is different story. Such phenomena will depend on the temperature. So depending on the temperature, for example, there are electron energy levels. Electron could be could be staying in the lowest energy state when the temperature is almost zero. But at room temperature, for example, room temperature, okay, temperature T is like on the order of like a 300K. 300K leads to certain thermal energy. Here KB is the Boltzmann constant. Then we multiply it by T, that's the thermal energy. Okay, thermal energy. If you put the room temperature into here, multiply by KB, then this energy will be like a 26 milli electron volt. So such a thermal energy will further excite the electron from here to somewhere else, depending on the energy separation. Actually, it is not that simple. It is not just like a 26 million volt. There is something called distribution. So if it is electron, then electron should be described based on Fermi drop distribution. Okay. So it will be discussed in Gangchen chapter 4, also later in this class. Important concepts that should be mastered through this chapter include the wave-particle duality, the Schrödinger equation, and the meaning of the wave function, the Pauli exclusion principle, quantum state, and degeneracy. Solutions of the Schrödinger equation for various simple yet very common potentials will be given. So Schrödinger equation include potentials. Okay, so it is related with certain energy calculation you can guess because it is related with potential. And when it is simple and common, then the solutions are available. Before we go into the topics of waves of matter, let me summarize the main difference between classical mechanics and quantum mechanics. Just like CM, classical mechanics has no proof, quantum mechanics cannot be derived. Okay? When it is derived based on certain reasoning, then we can say it is first principle. Yeah. But it is not possible in this case. The laws then that describe physics are ultimately proven by their ability to explain observation, not the way it is being derived mathematically. So surely it is mathematical, but we don't go through all the procedures to induce any equations of quantum mechanics, such as Schrödinger equation. It is not derived, but we just accept when it is proven by its ability to explain observations. So when the result of the calculation is matching with observations, then we just accept. In this sense, quantum mechanics borrows many concepts from classical mechanics. Classical mechanics is used for predicting the motion of large or macroscopic, which means it is the scale is much larger than de Broglie wavelengths or de Broglie lengths. De Broglie length is explained here. Okay. Often assumed to be macroscopic or large scale limit of quantum mechanics. So we solve quantum mechanics equations, but the scale is very large. Then the result will be becoming similar to those from classical mechanics, which is the meaning of correspondence. That is called as correspondence principle. Formally, classical mechanics is justified and applicable in the limit of h bar approximately or presumably to be 0. So if h bar is presumed to be 0, considered to be very small number, then we can apply classical mechanics. H bar, which is Planck constant divided by 2 phi, is written here. This is one of the most important constant in the nature, and usually engineers and scientists remember 6 by 6 by 10 to the minus 16 electron volt sec. Wave nature is ignored when it is in macroscopic scale, much larger than the Bohr wavelengths. In the macroscopic system or regime, the results of classical mechanics are acceptable. There's a typo here, sorry about that. Acceptable because the quantum mechanical wave nature of object is averaged out by the mechanism called decoherence. Coherence means we have description of waves. When you consider wave descriptions, we can think of something like cosine, right? Kx minus omega t, and there could be certain phase phi. If this phase pi is well defined, then we can call it coherent. And because we need to consider the wave properties, the phase should be defined. If the phi cannot be defined, then there could be like this kind of cosine wave, and different phase phi will lead to certain interference like this, so that eventually we cannot see the wave property anymore. So if the waves with different phase are mixed up, then we should see decoherence. Then we cannot see the wave nature anymore. So phase information or coherence is important. The process where the coherence is somehow removed, it is called as decoherence. Sometimes even large or macroscopic objects can show quantum effect, such as superconductivity, the Bose-Einstein condensation, superfluorescence. So if you are interested in those concepts, you can Google yourself. Right, and more detailed explanation is here. Especially many of the laws of physics are actually empirical. For example, gravitational force. We know the equation describing gravitational force, but that is just empirical. Okay, it is not derived, it is empirical, but it is correct, so we just accept. Classical mechanics breaks down when the dimension of the system is similar or smaller than the Bohr wavelength, which is defined h over p. P is the momentum. H bar is given here, and this value can be considered. This value can be considered to be 0. The uncertainty relation doesn't affect, since this is the uncertainty relation. Delta x is the position uncertainty. Delta p is the momentum uncertainty. We multiply them, then it should be no smaller than h bar over 2. But if h bar is almost 0, then this is 0. So now we don't have any limit of this delta x multiplied by delta p. The uncertainty relation doesn't affect anymore. Definitions of coherence. At any time the first wave changes, the second will change in the same way. So first wave is here. This is space. Second wave has the same phase, like this. Third wave has the same phase, like this. Then we can call them to be coherent, or we can say there is coherence. Okay. And we are actually very familiar with these properties of waves already. Electromagnetic spectrum. There is gamma ray, X-ray, visible from blue to red, right? And then IR and radio frequency. X-rays and visible light are just small parts of a spectrum of radiation, which extends from small wavelengths such as gamma ray, wavelength small here. Wavelength becomes large here. And we know the relation between wave speed and the wavelength. This is the wave speed, frequency, wavelength. So in the free space, we know that the speed of light is like a 10 to the 8 meter per sec. It will be replaced by mu and lambda. So for example, if we know the frequency, for example, frequency could be like 300 terahertz, for example, terahertz, 10 to the 12 sec inverse. Then we can calculate the corresponding wavelength lambda. I guess it will lead to some visible range of wavelengths with the 300 terahertz. I said terahertz. This relation is often used because sometimes people call certain range like 1 terahertz, 2 terahertz. That's the important frequency range these days. So corresponding wavelength calculation is sometimes necessary. Very useful number, a practical number, from energy equal to ha mu or h mu will result in eventually energy in the unit of electron volt, and then 1240 divided by wavelength lambda. This means that if the energy is, for example, 1.1 electron volt, which is the band gap energy of silicon, then we can calculate lambda. It will be on the order of like 1000 nanometer, as I said before. This is IR. Okay. For example, the band gap of gallium arsenide different semiconductor material, which is pretty important. The band gap is 1.5 electron volt at low temperature. So it means you put this number 1.5 here. into energy value. Then you can calculate lambda. Lambda can be calculated to be 820 nanometer. This is also IR. It means that gallium arsenide will be black in color. Okay? It means if the IR beam is incident into the gallium arsenide, it will be observed here. Observed means there will be many electron pairs in the material, and light cannot be transparent. Okay? And higher energy value visible. Actually, the band gap between conduction band and valence band, it is IR, and the higher energy is all observed here. Okay, the minimum energy. This is the there's no energy state in between, so light is not related with the transition. Okay. Yeah, in the case of band gap, but above the band gap, it will be observed. So visible, UV, yeah, such a spectrum, yeah, will be all observed. As a reference, I'm just listing up the electromagnetic spectrum here. So gamma ray, X-ray, extreme UV, near UV, visible, near infrared, moderate infrared, or mid infrared, some people call it, and then far infrared. This range is considered to be optics range. And then radio waves. This spectrum is discussed in terms of electronics. And those are summarized here. Yeah, the terminology or class of a spectrum and frequency relevant corresponding wavelengths, and then corresponding energy. They are interrelated in this way. So in this table we listed the names and their corresponding frequencies, wavelengths, and energies. Usually in optics one can cover from gamma rays to mid IR. Far IR in the middle, actually it was classically the range of optics, but nowadays already electronic devices can generate far IR, light, especially far IR. If you see this, it's on the order of terahertz. There are many terahertz devices, based on the semiconductors already. So these are now considered to be electronics. Right, that's what I'm saying here. Visible light can be easily generated from, for example, tungsten lamp, fluorescent lamp. But in other ranges, we need many different technologies, which we can't describe them all here. Yeah, this is absolutely different area. Yeah, so you can discuss discuss these topics in optoelectronics classes. We know radio waves are treated in electronics, but in broad terms, this is only a part of light, and thus it is sometimes classified into another area of optics. So actually, this is discussed in electronics, but these are also parts of light waves. So same principles, should be applied. Most fundamentally, Maxwell's equations will describe any of these ranges. As we know, in modern technology, we would like to cover the whole range with solid-state electronics or optoelectronics. Yeah, that's what we are doing actually. this range covered by devices, various electronic devices, and this is possible and actually feasible, all available from semiconductor devices. And these days, near UV and extreme UV, this range engineers and scientists are working on based on actually semiconductor materials. Another important point is the technological gap between conventional optics and RF. This is RF and conventional optics, and the gap was actually phi r, or in frequency it is called a terahertz technology, terahertz range, one of the frontiers in engineering. Wave-particle duality of light. We can find two examples from the textbook which show the wave-particle duality. Surely most of quantum mechanical problems are the examples of that duality. Here, first example is black body radiation. Second example is photoelectric effect. Black body radiation is explained further in detail. Let me first summarize these two different phenomena. Black body radiation. So the black body is something observing the light. There's no transmission, no reflection, that's why it is black. And when it's heated, there comes thermal radiation. For the thermal radiation, we can measure the light waves. Then we see that the phenomena can be explained only when the photon energy should be quantized. Conventionally, if we consider light waves, the energy is supposed to be, or presumed to be, continuous, but not anymore. Photoelectric effect means photon is incident into certain material, and there comes electric emission. In this case, the light is replaced by electron, and light behaves like particle. Okay, light waves should be treated now as particles. So wave, conventionally wave, and particle, they are now mixed. That's why we call it duality. The black body here is an object that absorbs all light that falls on it. No electromagnetic radiation passes through it, and none is reflected. Because no light is reflected or transmitted, the object appears black when it is cold. If the black body is hot, these properties make it an ideal source of thermal radiation. According to classical theory, Rayleigh-Jean's law, the black body emissive power should be inversely proportional to lambda, the wavelength which approaches infinity as short wavelength, as dashed line in figure here. So this black dashed line is classical theory, and colored lines are the experimental data. Temperature is changing, 5500 down to 3500 K. And this is intensity of emitted photons as a function of lambda. We see that classical theory doesn't fit. This classical theory presumes that the light waves should have continuous energy, and it doesn't work here in reality. The exact classical formula related with the Rayleigh-Jeans law could be found elsewhere. It is beyond the scope. Basically, we don't have enough time to go into the details of this. You can refer to any textbook, even Wikipedia will explain the details. To explain black body radiation, Max Planck introduced a radical hypothesis that the allowable or available energy of the electromagnetic field at a frequency mu, P is actually subscript, okay? It's not continuous, but it's a multiple of following basic energy unit. So there's a basic energy unit of H mu that is corresponding to energy. P is the photon, relevant photon energy. Should be H mu, where H is called as the Planck constant and has value of this one, and H bar we usually use and remember, shown here. This quantization implies that the atoms constituting the black body have well-defined energy levels. Well-defined energy levels which are discrete, and depending on the energy separation, for example, electron is excited here, it goes to the lower energy level, then there is light emission like this, and then this electron goes below, then again there is light emission. So if the energy levels are discrete, the emitted light should have certain fixed frequency. So, and this is the description of light waves in terms of now particle picture, and it is called as photons. Einstein's comments on this phenomena: electromagnetic radiation behaved as if it consisted of a collection of energy quanta or photons with energy h mu. The light waves have our well-defined quantized energy, just like particles now. So light waves, in terms of wave picture, now quantized like particle. Based on quantum mechanics, the photons are identical bosons with spin quantum number of 1. Thus, there could be many photons in the same energy state at the same energy position, since they are bosons. These are the properties of bosons. The exact number of photons, Ni, at certain energy, Ei, can be then described by a distribution function called Bose-Einstein statistics, as shown here. Ni equals to 1 over e to the ei minus mu over kt minus 1. Here mu is called as Fermi energy or chemical potential. Okay, and this k is Boltzmann constant. If we also accept that the energy of photons is related to its frequency by Planck formula, as shown here, under Bose-Einstein statistics, setting the chemical potential of Fermi energy mu to be 0 for convenience sake. Mu can be defined depending on materials. Okay? Which material do we really use? What kind of atomic compositions do we have? Then we can specify mu. But let's set it to be 0 for convenience sake. We would finally have this spectral equation on the light emission intensity as a function of frequency mu at a certain fixed temperature T, as shown here. So h mu and then ni, the number of photons at certain energy ei. Okay, so that is actually shown here. Distribution function will be plugged into here, and we go through integration. Then we have this, which is the same with the previous figure, colored line. This is the speed of light in a vacuum. K is the Boltzmann constant. So for mathematical details, you can refer to quantum mechanics textbooks, but we won't go through that details. And so this mathematical derivation won't be found in the homework or midterm exams in this class. Wave-particle duality of light, the photoelectric effect. It was found that when light is incident on one of two metal electrodes separated by a vacuum in figure 2.4a, a current can be generated in the loop. So this figure shows the experimental schematic. Light is instant. There are two metal pads, metal electrodes, and light is instant on one of the metal electrodes. The electron is emitted and accelerated. So the current is generated. We measure the current. It is explained here, but main idea is shown in figure 2.4b. There are two different energy levels. One is EF, Fermi level. The other is EV, vacuum level. Vacuum level means that at this energy level, electrons can move freely without Coulomb attraction with the atoms constituting the metal. And EF is defined like this. Please be careful. Only at T equals 0, absolute 0 temperature, you can say that EF is the maximum energy of electron. Okay, as shown here, this black shade means the actually electron reservoir So this is the energy levels, all different kind of energy levels. They are filled up to EF. But when you have non-zero temperature T, then you need to multiply it by K Boltzmann constant. Then that is thermal energy. As I said before, this is 26 milli electron volt at room temperature, which is the conventional temperature we operate our devices. And then there is thermal activation of caviars. And that will make it a little bit complicated to define this Fermi energy. In that case, actually, Fermi-Dirac distribution can exactly describe the meaning of Fermi energy. Okay, and it will be discussed later on. But in the very simple picture, for convenience sake, let's just say that EF is the maximum energy of electron. Okay, and their separation is work function. So electron is here. Instant light is the energy of h mu. If the energy is very small than this energy separation, okay, then the electron cannot excite into this EV, right? Only when the the frequency of the instant light is larger than certain value, certain threshold value, then electron will be excited here or higher. The electron can move freely to generate current. So this is the main intuitive picture. And this is the experimental result. This is similar to the intensity. You can say the current density. And this is frequency. And as we increase the frequency here, there's no current generation. And then above certain frequency range, it is increasing linearly. Okay. So these are actually the basic explanation of the phenomena. And Einstein reasoned that one photon can excite one electron out of the metal surface. That's important. One photon is replaced by one electron. Okay, so here light waves is now considered as a particle, which is replaced by an electron. Okay, only when the photon energy is higher than electrode work function pi. So the energy needs to be defined. So when it is discrete or quantum mechanics is involved, we can see that there are energy levels, separated, and relevant light emission should be the same with the energy separation. To explain this phenomena, Einstein introduced the concept of photon, particle picture or energy quanta of light. Photon is the elementary particle responsible for electromagnetic phenomena, thus a carrier of electromagnetic radiation. We call it carrier of electromagnetic radiation. The photoelectric effect can be simplified like this. Photons can be considered as particles with a specific energy of h mu. The electrons absorb the energy of photons only if photons' energy is larger than the work function W. This results in the threshold in the experiment. So work function W is equal to h mu 0. Electrons can escape the material with a finite kinetic energy. Kinetic energy T, M should be electron mass, V electron velocity, should be the same with h mu, incident light frequency, and mu 0 is the threshold frequency. No photoelectrons are ejected at light frequencies below the threshold, regardless of the brightness of the light. We also note that the light waves can behave as particles in the name of photons. In some situations, these experiments lead to the wave-particle duality of matter. So, light waves, that is the picture of wave, and photons, that is the picture of particle. So they have duality. Material waves. Wave-particle duality of light triggered Bohr, who was a graduate student then, to postulate that a material particle also has wave properties. On the basis of analogy of the Planck-Einstein relations, he proposed that every matter was associated with both a particle and a wave. The angular frequency omega and wave number k of the wave was related to the energy E and momentum P of the particle by energy equal to h bar omega, P equal to h bar k. Then you will see that P equal to h bar k, k is the wave number defined by 2 pi of lambda. Lambda is the wavelength. Then here into the numerator and denominator we multiply them by omega on both sides, and we move this 2 pi into the denominator. Then we see h bar omega is equal to energy, and here lambda wavelength, omega over 2 pi frequency, multiply them, then it becomes a speed. So we see that in wave picture, P is equal to E over C. The wave nature of matter was confirmed. For example, electron, which was considered as a particle, shows wave properties such as diffraction. Wave properties associated with macroscopic objects are totally insignificant because its wavelengths. Here you define the Bohr wavelength. It's like Planck constant divided by momentum. You can get it here. Based on this, you can get this. And macroscopic object, you can define, you can calculate momentum. Mass m, velocity v. Usually macroscopic object has larger value of mass than that in microscopic counterpart. Momentum p is very large, then wavelength lambda should be very small. If it is too small, then it cannot be measured. Yet the meaning of measurement is also depending on the resolution of your device. For example, spectrometer, monochrometer, and there is a resolution, like on the order of sometimes nanometer, sometimes 0.1 nanometer. So if it is much smaller than that, here wavelength is much smaller than the resolution, then we cannot measure it. When we cannot measure it, then why should we care? So it is considered to be insignificant. Even if they exist in principle, wave property might be existing, but still it is justifiable to ignore them and continue with classical mechanics because we cannot measure it. If P is smaller, P is small, lambda is large, then microscopic object has larger lambda, which corresponds to quantum mechanics regime. Since the wave-particle duality was confirmed, the mathematical equation for particles are now extended into equations of waves. Yeah, that's the actually starting point of quantum mechanical equations. Originally, we only had particle descriptions of matter, especially electrons are very important. So electrons were described in classical mechanics, but now it needs to be described in terms of waves. To handle this issue, we introduced the simplest form of waves called as plane waves. Then apply their waveforms. More specifically, we call it wave functions in quantum mechanics into Hamiltonian equation of motion. This is one of the important equations in classical mechanics, but we don't really need to know the details for now. But we can simply say that this is something like energy E is kinetic energy and potential energy. We sum them up. But more specifically, we represent kinetic energy with momentum, and we represent the potential as a function of this xyz coordinate, and this is also now is a function of p and x, right? In this case, if we consider p and x as independent variables, then we call this as Hamiltonian. Okay, instead of energy, we call it Hamiltonian. So the details are found in the appendix of J-Sing. Okay. So this energy is represented in particle picture. We replace it by we placed it into the wave picture. That is called as Schrödinger equation. We will discuss the Schrödinger equation from now on. Meaning of wave function. Propagating plane wave. So let's say f is a propagating plane wave formulated. Most simple case, it can be exponential function e to the I kx minus omega t, or cosine or sine function. If we take the real part of this, then we will have cosine function. If you draw down this curve, actually, it's pretty simple, right? So you draw this cosine function as a function of x, for example. Yeah. Then surely at certain fixed time, you can draw down the cosine waves. Okay, at t equals 0, for example. And then non-zero t is like a 10 second, 20 second, you can choose. And depending on the frequency values, later on, non-zero time, you can see wave is shifted like this. So it is actually propagating along the right direction, the positive x direction. And we can see that we only focus on x-axis, then why we ignore y-axis. Here we presume that everything is the same in y plane. Okay, that's the definition of plane wave. So plane wave can be found in any textbook examples, or you can simply Google it. the meaning of plane wave, then you can figure it out. Yeah, the meaning of this, this figure. So we are only considering x-axis and y-z-axis. Everything is supposed to be the same. In the Bohr wave picture, k is replaced by p over h bar. Omega is replaced by e over h bar. Then we now consider monochromatic wave. Monochromatic wave is the case when wavelength is fixed. So momentum p is fixed at p0 equal to h bar 2 pi over lambda 0. In general, wavelength lambda could be varied, and different wavelength value lambda could be mixed up. Then it is not monochromatic anymore. So we only consider the simplest case, simplest plane wave, and simplest monochromatic wave. Now considering an amplitude, pi, the matter wave is described based on propagating waves. Psi xt equal to amplitude pi, and then basic form of plane wave. Then this one, 1 over square root 2 phi h bar is the constant for normalization. Normalization has certain meaning. Here you see that you take the absolute value of psi and square, and then integrate it, then you will have 1. This is the definition of normalization. You can see that then this absolute value of psi square is similar to probability of statistics. Probability of statistics, right? And this is called as wave function in quantum mechanics, right? These are a little bit generalized explanation, but in this class we'll skip this part. So you can read through yourself. Something is missing or unclear, then you can leave comments, right? Operators and Schrödinger equation. So if lambda is fixed at certain value, we call it monochromatic. Then we don't need integration with different p values. So lambda is fixed, momentum is fixed, right? So for that momentum, pi is also fixed. So this is the wave function you have, right? And here, if you have spatial derivative round x, then you will see that original value of psi will be multiplied by, because we are taking the spatial derivative, we have I p0, right? So p0 over h bar, sorry, and then you can see that we multiply both sides by minus I, then just like this, and we multiply both sides by h bar, then we ignore this part, ignore this, we remove this, then we see that this is same with p0 psi. So if we take this mathematical operation, we have momentum value multiplied, psi. So this is very good mathematical operation to get the value of momentum. So this is called as momentum operator. Okay, so we indicate the operator by this symbol cap, okay, or hat. Alright, so we have now the meaning of momentum operator, and as I said before, psi square dx. Now consider probability, and more exactly probability of finding particle in the interval from x to x plus dx. This is normalization condition. When we apply the wave function now in terms of energy, we use a term Hamiltonian. So energy is shown here, and energy is just replaced by h here, but h is a function of p and x. Okay. When you consider energy in terms of two different independent variables of p and x, then we call it Hamiltonian. It is representation of energy based on momentum as established by Hamilton in classical physics. Energy is the most important value to determine in quantum physics, so we use the Hamiltonian representation of energy often rather than the position of velocity. The operator that induces energy value is now called as Hamiltonian. And from the wave function shape, this one, wave function shape, we know that simple time derivative induces energy values. So basic idea is this wave function psi. Now take this operation round t, then you will see that there is psi multiplied by minus I energy E over h bar. Right, so if you multiply I again, then it becomes minus I square, and then h bar on both sides, then this will be removed. Then you can see that it is easily energy then psi. So this is the operation to induce energy value, so it is called as energy operator. So in this case we call it Hamiltonian, okay, like this. So this Hamiltonian operator is equal to IH bar round t. Okay, it's sometimes called as Hamiltonian operator or Hamiltonian or energy operator in quantum mechanics. Time independent Schrödinger equation. This is actually one of the most important topics in quantum mechanics. In the case of potential free region, h cap psi or h hat psi is equal to IH bar round t psi. It's inducing that energy part, right? And others are just psi. When it is potential free, we only have kinetic energy part, p square over 2m, right? And this p square can be also replaced by operators. So p square is replaced by this one, minus IH bar round x square, and then we'll have this one minus, right? So this H cap is corresponding to this operation now in potential free region. In the case of in the case with potential Vx, then this operator, okay, this one is now replaced by this one. We simply add the potential. So that is now the Hamiltonian space description. Yeah. So H cap or H hat is the energy operator. In this class, let me just name this as H cap, through which you induce energy value. The eigenvalue equation for H cap is Schrödinger equation. So H cap psi is equal to E psi. And in time independent Schrödinger equation, we replace it by this operator. So this is actually something we'd better remember. It will be repeatedly discussed. So basic idea of this class is, for given potential shape Vx, how can we calculate energy value E? That's the key of this class. When the potential V is very complicated, then we use some approximations, that is variational method and perturbations. It will be discussed later on. Here we ignore time-varying terms for wave functions. We call this as time-independent Schrödinger equation. So, time-independent Schrödinger equation in one-dimensional case. In three-dimensional case, we expand this into gradient square or Laplacian, and then this psi xt is now replaced by R vector and t. So, and also the wave function psi has the t dependence. So psi t, which is a function of t and r, indicates the time dependent wave function, and psi r is time independent wave function. In simplified cases, because we presume that we consider a monochromatic case, the psi t equal to this one, time independent part multiplied by time varying part, okay, e to the minus I e t over h bar, okay. Right, so if you calculate energy value here, this one is corresponding E psi, okay. This is time dependent Schrödinger equation because we added this part, and it is supposed to be same with E psi, and we calculate this time independent Schrödinger equation ignoring this t dependence. Then we calculate energy E. Then we multiply psi r by this amount, then it becomes time dependent wave function. Here we added time varying terms for wave function. We call this as time dependent Schrödinger equation. This is time, this one, time dependent Schrödinger equation. In simple case, we first calculate the energy and time independent wave function, then multiply it with a varying term with this. Schrödinger equation measurements in quantum mechanics. Since this one, wave function psi and complex conjugate psi star, we multiply them. That means we take the square of absolute value of psi. It's actually probability. Subscript T might indicate information of quantum state such as quantum number, which we will learn soon, not only the time. T could be time, but sometimes it could be quantum numbers. Okay, it will be discussed later on. The quantum world is full of uncertainties. Any quantities such as energy, momentum, and location are no longer a deterministic quantity, but have an average or expectation value. So let me remove this expectation value and uncertainties. The expectation value or most probable value of any quantity can be calculated by applying operator onto wave function. So how can I get it? Like this. This is the meaning of average value. Okay. Right. So for example, we are familiar with the momentum operator. This is the momentum operator. Then what could be the expectation value of momentum? So this is the way we calculate that. We know the energy operator as shown here, or this one. These are the energy operators. Then this is the expectation value of energy. Just like that, we apply it into potential. We apply it into location. Okay. When you get it, mathematically, then we also measure the position of the particle repeatedly and then average them. This is the mean value of position. And this is the same with the expectation value of quantum mechanics. And it was proven, so that's why we just accept. Schrödinger equation, uncertainty. Because psi star psi is a probability, and the physical observable quantities are only the expectation values. There are also standard deviations. Because now things based on wave functions, and we need to consider probability. Then, all those ideas can be found from the statistics. In statistics, there is something called standard deviation and average value. So standard deviation in location delta x, and standard deviation in momentum delta p, standard deviation in energy delta E, standard deviation in time. It can be proven that for any solution of Schrödinger equation, the following relationship holds. So it is actually mathematically proven. Okay. So the standard deviation in momentum multiplied by standard deviation in location is no smaller than h bar over 2, no less than h bar over 2. Likewise, delta E by delta T, no less than h bar over 2. In statistics, standard deviation is defined like this. So delta x square is this one is the symbol indicating the average. So This is position and this is the average value of position. Yeah, separate them and then take the square and then take the average. So, for example, if delta x is 0, so the electron is fixed at certain position. Okay, is it happening in materials? Actually, yes. Even though you have very good semiconductor material where carriers can move freely, but there is certain point where atom is missing, or some crystal structure is broken, then there is something called localization trap. So the energy state is abruptly changing at a certain position. This scale is extremely small. The carrier is trapped here. So it is like localized state. And let's say it is not actually extremely small. It has certain scale. But that scale is supposed to be, let's presume it to be very small, like like a single atomic scale. Then momentum uncertainty from this principle, if delta x 0, there is a finite number. This should be infinity. So if the position x of a particle is known precisely, the momentum p of the same particle is completely unknown. Yeah, it happens actually. So momentum of the electron in such trapped state cannot be defined. Okay? Quantitatively in wave picture, even if an identical experiment involving an electron, E, is performed many times, and in each run of the experiment, the position x of the E is measured, then although the experimental setup is identical in each run, measurement of the position E doesn't give the same result, so it means delta x isn't 0. Right? If delta x is small compared to some typical lengths in the experiment, one is more certain to find the value x in any given run. Delta x is very small. If delta x is large, then it is not certain what the measurement of x will yield. For this reason, delta x is called the uncertainty in x. So in Schrödinger equation, when you consider Fourier transform, actually uncertainty occurs because delta x and delta px are correlated with each other through Fourier transform in wave picture. Matter is now represented by waves, more generally by sum of waves, but we will only consider single wavelength case, monochromatic case. Consider a matter wave as shown here. Now let's say it is represented in K space, okay? K space, represented by this pi K, okay? And the relationship between psi and pi is the Fourier transform, right? Fourier transform. So here phi k is given like this, right? When you consider, just as an example, let's say wave function happens to be this Gaussian, and when you take the Fourier transform of Gaussian, it is also Gaussian. And look at this function. Actually, wave function in real space, this is the wave function in K space. When you draw down this curve, psi is like this. It is centered at 0. It has certain width, right? Like this is half value. So full width at half maximum, we usually call it. Then that is some intuitive measure of delta x. It is on the order of like alpha. Surely there will be certain weighting factor here, but it will be on the order of alpha. And this one, if we draw down the curve in K space, also it is centered at 0. And here there's a full width and half maximum. Then you can consider delta k. Look at this. Here delta k is similar to the 1 over alpha. Similar to 1 over alpha. So if we multiply them, it is on the order of 1. So if we multiply both sides by h bar, then h bar k is the momentum. That's the way you can see delta x, delta p is on the order of h bar. Exactly speaking, if you calculate more carefully, then the exact value is actually like this, h bar over 2. So Gaussian is the case when you have the minimum uncertainty. Okay. The point here is delta x, delta p is larger than certain minimum value. And uncertainty is minimized for Gaussian shape waves. More precise treatment of statistics results in delta x, delta p is no less than h bar over 2. And these are homework problem sets. You can calculate yourself, and due date is the next Wednesday. Right? That's it for today.